What if a million users hit this button all at once?
Yeah,
I mean, if your Napkin math shows that the database will take like 3 years to process that,
yeah.
you don't need to build it to know it's a bad design. You've saved yourself months of work in 5 minutes.
So today, we are going to build your toolkit. We'll cover the three pillars Alex Yu lays out: powers of two, latency numbers, and availability nines.
Hmm.
And then we'll put it all to the test. We'll run a real simulation, an interview question about Twitter, and see if we can calculate its storage needs right here, on the fly.
It's going to be a fun mental workout.
Let's start with the first tool in the kit, the powers of two. Now, I know most of us, we think in base 10, 1,000, 10,000, 100,000. The computers just don't think that way.
No, they don't. At the lowest level, everything is binary. You know, a byte is 8 bits. So when we talk about storage or data volume, the math doesn't scale by tens, it scales by powers of 2.
And this is why I think a lot of people get tripped up, especially in those high pressure situations.
Oh, for sure.
You're trying to convert gigabytes to bytes in your head, and the zeros just start swimming.
That's where you suggests just memorizing a cheat sheet, a set of approximations. You don't need to be precise, you just need to be fluent.
So walk us through that. Where do we even start?
Okay, it all starts at 2 to the power of 10.
2 to the 10.
Now, technically, that's 1024, but for this kind of math, just call it 1,000. That's your kilobyte.
Okay, that's our anchor. 2 to the 10th is 1,000.
Now just jump up 10 more levels. 2 to the 20th. That's 1,000 times 1,000.
A million.
1 million. That's your megabyte.
So 2 to the 30th.
That's a billion. A gigabyte.
2 to the 40th.
A trillion. A terabyte.
And the big one? 2 to the 50th.
1 quadrillion. That is a petabyte.
It seems so simple when you lay it out like that. You're just adding 3 zeros for every 10 powers.
Yeah.
But why is this so critical? Why not just say a lot of data?
Because the inputs you get in a design problem are usually mixed. They'll say you have 10 million users, which is a base 10 number,
Right.
but they're uploading 2 ME files, which is base 2. If you can swap million for 2 to the 20th in your head, the math just becomes incredibly fast.
You're just translating everything into a common language so you can multiply without a calculator.
Precisely. It lets you speak the language of scale fluently. You can focus on the architecture, not the arithmetic.
Okay, so we've got volume down. We can speak in petabytes, but that's only half the equation. We also need to talk about speed.
Speed is huge.
Latency numbers every programmer should know.
It basically lists how long a computer takes to do, well, anything.
And it's all measured in nanoseconds.
Yeah, nanoseconds.
Which is a unit I can't really wrap my head around. A nanosecond is 1 billionth of a second. It just feels instantaneous.
It does to us humans. But to a computer, the difference between 1 nanosecond and 10 million nanoseconds is like the difference between blinking and waiting for a glacier to melt. The scale is just massive.
So let's walk through that spectrum from the blazing fast to the painfully slow. What's at the very top?
The L1 pass reference, this is the CPU's own little memory. It takes about half a nanosecond.
Half a nanosecond. So effectively
Yeah. Then you step down to L2 cache, that's around 7 nanoseconds. Still incredibly fast.
Okay. What about when we actually want to do something in code, like locking a mutex?
Now you're at 100 nanoseconds, and it's about the same for reading from main memory from RAM.
So 100 nanoseconds to read from RAM. That's our baseline for fast but not instant.
Right. Now here is where things get really interesting. Let's talk about compression. Compressing 1 kilobyte of data with a fast algorithm like Zippy, that takes about 10,000 nanoseconds.
Which is 10 microseconds.
Yes. Now compare that to sending 2 KB over a 1 Gbps network. That takes 20,000 nanoseconds.
So compressing the data is actually,
Yeah.
it's twice as fast as just sending it.
In this specific comparison, yes.
Yeah.
And that leads to one of the huge takeaways from this chart. Compressing data before you send it is almost always a win, right? You're trading a cheap resource, CPU time, to save an expensive one, network bandwidth.
That's a great rule of thumb. But the real villain of this whole chart seems to be the disk.
The disk is the absolute villain of performance. A disk seek moving that little mechanical arm to find data on a spinning platter takes 10 million nanoseconds.
10 million. We went from half a nanosecond in the cache to 10 million on the disk.
It's a factor of 20 million. That's why the number one rule of high-performance systems is so simple. Memory is fast, disk is slow. Avoid disk seeks if you possibly can.
That number just puts everything in perspective. If your design has to hit the disk for every single user request, you are dead in the water.
You're just building a traffic jam.
And there's one more number on here that blew my mind. The round trip from California to the Netherlands.
150 million nanoseconds.
150 milliseconds.
It sounds fast, but in computer time, that is an eternity. It reminds us that data centers in different regions are not neighbors. The speed of light is fast, but it is not infinite.
Right.
If you're sending data back and forth between, say, Europe and the US, that latency adds up incredibly fast.
So we have volume the powers of 2. We have speed the latency numbers. The third tool in our kit is reliability.
The availability numbers. This is where we get into SLA's service level agreements. You know, if you're Amazon or Google, you are promising your customers a certain amount of uptime, and that promise is measured in nines.
And I feel like this is one of those marketing terms that actually really matters. Yeah. Because to an average person, 99% uptime sounds fantastic.
Oh yeah, sounds great.
If I clean my house 99% of the time, it would be scoutless.
99% is... it's actually terrible.
Okay, walk us through one.
All right, let's just do the math. There are 365 days in a year. If you have 99% availability, that means you have 1% downtime. What's 1% of a year?
About 3.65 days.
Imagine if Netflix was down for almost 4 full days every single year.
People would riot.
They would. 4 days is a lifetime in tech.
Okay, so let's add a 9. 99.9%. 3 nines.
Now your downtime drops to about 8.7 hours per year.
That's better, but still almost a full workday of an outage.
It's acceptable for some services, but probably not for your critical infrastructure. So we go to 4 nines, 99.99%. Now we are talking about 52 minutes of downtime per year.
Less than an hour a year. That feels like a really solid target.
It is. But the holy grail, what the big cloud providers are often aiming for, is 5 nines. 99.999%.
What does that translate to in actual time?
5.26 minutes.
5 minutes of downtime in an entire year.
That's the difference. And if you go to 6 nines, you're allowed 31 seconds of downtime per year.
It's just wild. The difference between 99% and 99.999% looks so small on paper. It's just a few decimal points. But in reality, it's the difference between a broken system and a world-class one.
And it is exponentially harder to get those last few nines. Every 9 you add probably doubles or triples the cost and complexity of your system.
All right, so we have our toolkit. We understand units, we understand speed, and we understand reliability. Now I want to put us in the hot seat. Let's do it. Estimating Twitter. Now, obviously, these aren't the real internal numbers from Twitter HQ.
No.
But they're a great set of assumptions for a thought experiment.
Right. So picture the whiteboard. The interviewer says, I want you to estimate the queries per second, the QPS, and the media storage requirements for Twitter.
Where do you even begin with that?
You begin with assumptions. You can't calculate anything without variables. So, assumption 1, 300 million monthly active users. 2, 50% of them use Twitter daily. 3, users post, on average, 2 tweets per day. 4, 10% of tweets contain media. And 5, we store all this data for 5 years.
Okay, that is our universe. Let's tackle a QPS first. How many tweets are hitting the system every second?
Okay, so step 1 is getting to daily active users. If we have 300 million a month and 50% of them are daily.
Right, so half of 300. That's 150 million daily users.
And if they each post 2 tweets,
150 million times 2 is 300 million tweets per day.
Correct. 300 million tweets a day. Now, to get to QPS, we need to divide that by the number of seconds in a day.
And this is where I normally pull out my phone.
But you can't. So how many seconds in a day? 24 times 60 times 60. It's 86,400.
That is a disgusting number to try and divide by in your head.
So don't. Round it. This is the whole point. Call it 100,000.
Wait, we can just do that. Just round 86,000 up to 100,000.
Absolutely. We're looking for an order of magnitude, not a tax return. It makes the math so much cleaner. So 300 million divided by 100,000.
Okay, so 300 million has 8 zeros. 100,000 has 5 zeros. We just cross off 5 zeros. We're left with 3,000.
And the text says the precise answer is about 3,500. So 3,000 is a perfectly good estimate.
That feels amazingly like cheating, but I will absolutely take it. Okay, so 3,000 tweets per second.
That's the average load. But as we know, the internet isn't a flat line. You know, everyone wakes up or the Super Bowl happens.
Right.
So we need to estimate peak QPS.
Is there a standard multiplier for that?
The common rule of thumb is just 2x. So if your average is around 3,500, peak is around 7,000.
Okay, 7,000 QPS, that tells us about throughput. But now we have to figure out where to put all this stuff. The storage estimation.
This is the heavier lift. We know we have 300 million tweets a day. But text is tiny, right? 140 bytes is nothing. The real cost is the media.
And our assumption was 10% of tweets have media, and that media averages 1 millibeat.
Exactly. So take our 300 million tweets. What's 10% of that? 30 million. So we have 30 million tweets with media every single day, and each one is 1 megabyte.
Okay, so 30 million times 1 millibeat is 30 million megabytes.
Please, your power of 2 ladder.
Okay, a million megabytes. Well, 1,000 MB is a GB. A million MB is a TB, so 30 million megabytes is 30 terabytes.
Spot on. 30 terabytes of new media generated every single day.
There's a lot of hard drives. But we aren't done. We need to store this for 5 years.
So the final math. 30 TB times 365 days times 5 years.
Okay, let's simplify again. 30 times 365, that's roughly, what, 11,000?
Roughly.
And 11,000 times 5 years, is 55,000.
So 55,000 terabytes.
Geez, 55 petabytes.
There it is, 55 petabytes. You just sized the storage layer for a major social media platform in, 60 seconds of mental math?
It's incredibly satisfying when you get to that final number.
So what I have to ask,
we did a lot of rounding there. I mean, we rounded seconds in a day. We basically rounded days in a year. Doesn't that make the final number wrong?
It makes it approximate. And that brings us to the art of approximation section of the chapter. Alex Yu gives some really specific tips on how to handle this without looking sloppy.
What's the first two?
Process over precision. The interviewer knows that 300 million divided by 86,400 isn't exactly 3,000. They don't care. They want to see that you know how to set up the equation.
Huh?
If you waste 5 minutes doing long division to get 3,472.222, you've actually failed the test.
You missed the forest for the trees.
Exactly. It shows you don't understand trade-offs. You're prioritizing a kind of precision that just doesn't matter here.
So, tip number 1, round aggressively. What's number 2?
Write down your assumptions. We listed all those variables at the start, 300 million users, 10% media, and so on. You have to write those on the whiteboard.
Why is that so important?
Because it's your contract with the interviewer. If you get 55 petabytes and they say, that seems high, you can point to the board and say, well, that's based on the 10% media assumption. Do we want to lower that?
It turns it into a conversation.
Yes, it's a conversation, not a pass-fail on the final number. It protects you and shows your work.
Okay, and the third tip.
And honestly, this is the one that saves people's careers. Label your units.
Oh, I am so guilty of not doing this. I'll just write down 5 or 5,000 and hope I remember what it means later.
And you won't. In the heat of the moment, you'll look at that 5 and you will forget if it's 5 megabyte or 5 gigabyte. And if you confuse those two, your whole design is off by a factor of 1,000.
Which is a catastrophic failure.
It is. The text is very clear. Always write the unit. 5 millibeat, 30 TB. It just reduces the cognitive load on your brain.
That's great advice. It's about freeing up your brain to do the actual thinking.
And finally, the text suggests knowing your common targets. In almost every system design interview, you're going to be asked to estimate the same few things.
What are the usual suspects?
QPS, peak QPS, storage, cache requirements, and the number of servers needed. If you practice estimating just those 5 things, you'll be ready for 90% of the questions out there.
It's like practicing scales on a piano. If you know those, you can improvise the rest.
Exactly right.